We have seen a couple of examples on some very hard problems. In this clip, I will briefly discuss a couple of general techniques for dealing with computationally hard problems. The general techniques are referred to as heuristics and approximation algorithms. Let's take a closer look at both. The main idea is to reduce computation time, but at the cost of losing the accuracy or precision of the found solutions. This increased computation speed is obtained by cutting some corners, but sometimes this corner cutting may result in simpler algorithms that are easier to understand. We have actually already seen a couple of examples on heuristics. Recall the greedy algorithm that always traverses along the steepest part of a curve in an attempt to find its maximum value. This is sometimes referred to as the hill climber heuristic. The drawback, however, was the risk of the algorithm to get stuck at a local maximum before reaching the global maximum. If the algorithm instead accepted going in the wrong direction but with decreasing probability for each iteration, then it might be able to escape a local maximum. That approach is referred to as simulated annealing. A completely different strategy for finding a solution to a problem could be to initially generate a set of completely random solutions, which may be far from the optimal solutions. Now we enter a loop in which we select the best few solutions from our solution pool. Then a bunch of new solutions are generated by randomly mutating the selected solutions. The worst solutions are deleted from the solution pool, leaving us with a probably improved set of solutions. The loop is repeated until an appropriate stop criteria is met, for example, until the solutions are good enough or a certain number of iterations has been executed. Maybe not that surprisingly, these kinds of heuristics are referred to as genetic or evolutionary algorithms because of their familiarity with how evolution works in nature. Last, consider this graph, which could represent cities and roads connecting them. A way to reduce the computational complexity when calculating the length of the shortest route between the two orange nodes or cities is to calculate a part of the route precisely and estimate the rest. Clearly, the more of the route that is calculated precisely, the more precise is the total computed distance. For a routing algorithm that inspects the most promising nodes first, this estimation technique can be used to guide the algorithm to not waste too much time on nodes that leads to a route away from the destination. That is, with a good guidance, the algorithm can quickly come to a solution that is close to the optimal solution. And this is indeed a key concept in the so-called A-star routing algorithm. Approximation algorithms share the same basic purpose as heuristics, namely trading accuracy for computation speed. Approximation algorithms are used for optimization problems, which are about maximizing or minimizing a certain value. For example, maximizing the combined value of items in the knapsack problem, or minimizing the route length in the traveling salesman problem. Heuristics, on the other hand, is a more general term for the algorithms that solves a problem faster by slacking accuracy. For example, a heuristic could also be used for estimating solutions to a decision problem. So, like heuristics, approximation algorithms run in polynomial time, and typically the exponent will be very small. The important key property of approximation algorithms is that the amount of accuracy is mathematically provable. That is, there is a hard limit on how poor a solution the algorithm will produce. And this is incredibly useful in situations where a hard problem needs to be solved, but where only a certain distance to the real optimal solution can be allowed. As an example, consider this graph representing all possible solution values for some optimization problem. Here is the maximum value, which would be the value of the optimal solution. An accurate algorithm would eventually find that solution. Approximation algorithms operates with an error factor, here named p, that specifies the amount of allowed inaccuracy. P is a number between 0 and 1, and typically P is very close to 0, indicating that only a very low amount of error is allowed. And this means that the approximation algorithm would be guaranteed to find a solution within this orange band. And often this will be sufficient. For example, if P is 0.05, corresponding to 5%, then the found solution of the maximization problem will have a value of at least 95% of the optimal solution. Similarly, for minimization problems, this would be the minimum value and thus correspond to the optimal solution. For the allowed error P, an approximation algorithm will find a solution with a value within the orange band. This means that the found solution will have a value that is at most 5% larger than the minimal and optimal solution value. And, as mentioned, this imprecision is bounded with a mathematically provable guarantee. One category of approximation algorithms is referred to as polynomial time approximation schemes, or just PTAS. For PTAS algorithms, there is an explicit relation between the allowed error P and the algorithm complexity. The relation could, for example, look like this. If P equals 0.1, corresponding to an allowed error of 10%, then the complexity would be n to the power of 10. And if P was equal to 0.05, corresponding to an error of 5%, then the complexity would be n to the power of 20. So, when P approaches 0, 1 divided by P grows quickly. The point of PTAS algorithms is that the very same algorithm can get arbitrarily close to the optimal solution by providing it with a sufficiently small p-value. The cost, however, is that the complexity will grow as p approaches 0.